My name is Hanhee. I actually moved to Chicago in September as a new executive that covers Illinois. But my other half of the work is also covering the quantum strategies in Japan. And plus, I also am responsible for the global university research program for IBM for quantum computing. But today, again, I will show you a little bit of our activities and then our vision through the National Quantum Algorithm Center, and also how IBM's been pushing technologies in the past few years. And then also like a future of computing. I mean, I guess title is the quantum-centric supercomputing, which is the quantum and HPC and then GPU all integrated as our, that's actually our vision for the future of computing. So I'll show you a little bit of that at the end of the talk. But IBM mission is, especially for quantum computing, we'd like to bring the useful quantum computers in the world. And we've been engaging with a lot of Illinois, I mean, already in the Illinois quantum ecosystem as early as 2019. Well, I guess I wanted to point out that the first activities here is 2019. We joined the quantum Chicago Quantum Exchange. Thank you for throwing this the summit. And we started this postdoc program. And then it was a massively successful. I wanted to call out Kate Smith. I don't know whether Kate is here, but she's like one of our star postdocs who went through this program and then started the quantum research group at Northwestern. Thank you. And of course, I mean, I think these kind of summarize our activities in Illinois. So I just wanted to show you that we've been contributing to the Illinois quantum ecosystem growth as early as 2019. And of course, our major research partnerships is through the UIUC and U Chicago. And then we both schools we are funding for research, and then we are doing the research together. And at the last year, our CEO over there is Arvin, and then Jake Gambetta is our VP of actually right now he's a director of IBM Research. We committed to partner with the state of Illinois to build together with IQMP the National Quantum Algorithm Center to push the development of the quantum algorithms for industry and science. And for that, I think IBM has been again really pushing to accelerate and then advance the quantum computing capabilities to bring you to for the research and industry. And these are actually sort of I'm showing the key milestones that how we are getting there. And then in the basically like a plan for the in the next 5 years. We actually started in 2023 that's showing the quantum computer is actually useful. So quantum computer can be used as a part of your research tools with a 100 plus qubit system. So we call it as a quantum utility. Next year, we are working really hard with all our partners, including our partners in Illinois and then at Globe, to demonstrate the quantum advantage. And our team is also pushing really hard to bring the first error-corrected quantum computing system to demonstrate that in 2028 and then delivered in 2029. So how IBM has been contributing to really push the latest or the best quantum computing systems in the world. So I'll just show you some metrics here. These are sort of the latest numbers. I just want to call out that the IBM quantum computers operate 1,000 times faster than any of the computing systems in the world, which is very important because computing time is that's actually money that you have to spend, and also how fast you can get the results using the quantum computer for your mission and the usefulness. But at the same time, I think a lot of people are familiar with the quality or the error rates for 2 qubit gates or occurrence times, but our quality is also one of the best if you're comparing, especially in the 100 qubit system, the level. So I wanted to show that's the kind of summary of it. And then what is the software? Our software, the Qiskit, is our software development kit, and it is 83 times faster with the new translation techniques. And we can also reduce the 2 qubit gate in our quantum circuits quantum program, which is actually most expensive part of the quantum program. We were able to reduce by almost like 30%. And that actually shows as a result, if you see that graph there, then Qiskit is one of the largest dependent projects in the world compared to the other software, so the other SDKs available in the world. And we are trying to bring that quantum computing capabilities that we are pushing hard to the users. And we have 9 computers. Actually, we have we've been deploying more than almost close to 90 systems so far that if we deploy through our data centers. We also have 2 data centers in the world, one in the Poughkeepsie in New York and another one in Europe, in Germany. And of course, we are also deploying 9 quantum systems in different locations. Like right now, we have 7 systems already deployed, and then 2 more systems to come. And then those are deployed to different centers of the client sites that people can use the quantum computer the on-site. And of course, this kind of effort is showing up as adoption by the users. And you can see the service users are continue growing, and it's almost 200,000 the service users. And our IBM Quantum Network is the network of our partners and clients. So more than 300 members in IBM Quantum Network. You can see the logos there that basically all other major universities and industries are participating and working with us. I especially wanted to call out that actually right now the IBM quantum computers are also helping on the business. So this is a startups that we are working together. And there are 93 startups in IBM Quantum Network. There are 54% of the quantum software companies are part of the IBM Quantum Network. And there are 84% of the total quantum software venture funding is captured by the startups in the IBM Quantum Network, which is kind of remarkable. So this is actually showing the metric that how the quantum computing is bringing business to the world when you have a performant quantum computing system. So this quantum computer will coming to also Chicago in 2026. So that's a part of the IQMP. It will be in the Hyde Park Lab near the campus of the University of Chicago. So through all these advanced quantum computing capabilities, in Illinois, our mission is we wanted to partner closely with the National Quantum Algorithm Centers to accelerate the development of the quantum algorithms and applications, especially using quantum computing, and then also HPC together. Because a quantum, HPC, GPU, all the computing systems integrated is our vision for future of computing. And we'd like to realize that through the National Quantum Algorithm Centers. And there are 2 paths for it. Like one is we specifically rigorously prove the quantum advantages. But of course, we also need to empirically test the usefulness of the quantum computing systems. And what is a quantum advantage? I guess there are a lot of the definitions of this. And then I think this kind of summarizes a little bit of the higher level. And to show the quantum advantage, we have to show the result is correct, right? Like we can just solve something really hard and then there's some outcome there. But if you don't know that the outcome is correct or not, then you cannot really call it as a quantum advantage. But also at the same time, the computation itself has to have some advantage. Like it says as a quantum separation, that quantum computation has to be showing some advantages cheaper cost or efficiency in the computation, or higher accuracy than existing methods. And this graph is showing where we can see the quantum advantages even before we actually can bring the fault-tolerant quantum computers. And these are the areas that we think that we can explore quantum advantage in the next 5 years. Hamiltonian simulation is basically including chemistry, physical systems, and material computations. We are especially working in this area together, integrating quantum computer with HPC. Optimization is another part. I know that optimization has a lot of great classical algorithms there, but you can actually check the white papers because they are definitely the areas that quantum computer can help the existing optimization algorithms. And quantum machine learning and partial differential equations is sort of the more longer term, like the topics that we are also kind of exploring. But of course, on all these areas, we are working very close with many different partners. And then we are hoping to, again, work with a lot of partners through the National Quantum Algorithm Center. And maybe the last part is the quantum-centric supercomputing. I wanted to show like where we are going for the future vision. Again, quantum-centric supercomputer is the integrated system with a quantum computer and then CPU and then also GPU. And then we have to actually develop the specific algorithms for this kind of systems. And we are like, it's not just a vision, actually we are realizing our vision, and especially our partners in Japan and then RPI. We already deployed like 3 quantum-centric supercomputers in the world that is actually being serviced to the users. Actually in Japan is very active. RPI, they are using it for their research systems with their HPC system in the campus, on campus. And the RIKEN and University of Tokyo, we just finished the integration there. Is using IBM quantum systems to connect to Fugaku, one of the fastest supercomputer in the world. And the Miyabi system is the GPU. And then these are actually start being serviced to the industries in Japan. And I just wanted to show that it's like, the integration is not that difficult, or it requires, not that difficult means it is something that we can actually work on it. This requires software development. For systems that we are using in RPI, we had to use the Qiskit runtime API, so just to connect the HPC directly to our quantum computer. So there's like an interface the clients needed to build. And for RIKEN also do the same thing, but RIKEN is also already very advanced HPC center that they were able to work with us to develop the libraries and schedulers, so job schedulers, to connect our system to their Fugaku supercomputer. And for the Miyabi supercomputer at the University of Tokyo, we were actually using through the IBM quantum platform, IBM Cloud. And then this was also like connecting through the API that we just worked with IBM software team and then the University of Tokyo software team to develop together. And so the key thing about developing the quantum-centric supercomputers and then also service that is job scheduling, and then how we flow the data, and then also manage the resources. And for those, we are using the open source software platform. One is a Slurm, and then the other is the Prefect. Slurm is the resource management system that is open source that used by many of the HPC users. And then Prefect is the job scheduling, job management systems that a lot of people are using, especially in the AI, the AI field. And with that, also we were able to open our quantum computing to completely different the communities, like on HPC communities or AI communities here. So using actually the RIKEN system, just one demo that we are showing, which actually hasn't we actually submitted to archive last Friday, and then it will show up. So please look up. We were able to solve the FE4S4, which is one of the difficult molecular systems to solve. And then, of course, there's approximation methods is there, and it's not possible, of course, the brute force methods. But we were showing the quantum and HPC algorithms. It's called the sample-based quantum diagonalization algorithm to sample the quantum states in a quantum computer, and then using that sample the wave function to diagonalize to obtain the Hamiltonian in HPC, such that we were able to compute the ground state and the ground state energy for this molecule using the quantum-centric supercomputer. So it's one of the first few examples of how we can use a quantum and HPC. And of course, in the behind, we were able to develop all the workflow and then the algorithms in the back. And then, this kind of graph shows that we were able to, it's much large, a very big computation that we have to compute 10 to the 10 determinants for this. So I don't think this is a video, but again, I think in 2028, we are trying to demonstrate, or we will demonstrate the first error-corrected system in the world, which is called Starling. I think I'm not sure Jerry Chow is here, but our head of IBM Quantum, like a hardware will be here. So if you can ask that question, that will be 200 logical qubits that can execute 100 million quantum circuits, and it's like actually it's the size of the little bit of the tennis court if you kind of look at it, and by 2030 plus. We will also bring IBM Quantum Blue Jay. This is another system that will have 2,000 logical qubits with the 1 billion the quantum gates. We have a white papers that how we can build this system in the archive, and also this uses the latest error correction codes that has a much lower overhead between the physical qubit and the logical qubit. So everyone at IBM is pushing towards to develop or realize this system. And again, I'm hoping that using these IBM quantum capabilities, I hope that we can develop the quantum algorithm, explore the quantum algorithms and applications together, such that we can also advance our research, and then also, of course, bring business to the Illinois region. So for that, I guess I just want to show the size of the systems are kind of this. So anyway, thank you so much for your time and for listening to my talk. And then anybody want to explore Qiskit, just get the QR code here. So thank you.
Yeah, thank you for the amazing talk. My question is, after error correction being realized, I guess after 2030, for how long do you think there is still enough market for the non-error corrected algorithm?
So quantum algorithms doesn't really matter whether error correction or not. I mean, of course, with error corrected systems, you will be able to run much deeper circuits. Algorithm should be the same. I mean, algorithm is algorithms, right? And then how you implement in the quantum systems will be different. So, I mean, without the everything will be continually used. I mean, even error mitigations and a lot of techniques that we are developing, those will be continually being used even after error corrected systems are bringing it up.
Do you know if IBM is going to be improving their topology, i.e. the qubit to qubit connectivity channels, and is that going to make logical qubits? If you expand that to more dimensions, will that make logical qubits easier to build?
Yes. So for Starling, we'll use a 6-way coupling, which I didn't really show, but we demonstrated it last year. And because of that, we were able to actually reduce the overhead from surface code to this new LDPC code. And before then, we are also trying to bring Nighthawks, which is like a square lattice system, also just for convenience. But yeah.
Thank you. Great talk. I'm curious if there's a lot of focus on the hardware side of things because that's where we are kind of optimizing the problem. But on the roadmap, what about the software side and how there's a massive undertaking for enterprises to move to a quantum-ready software of the future? Is it time to start thinking about that in different use cases, or will that time come later when we prove the concept can work? Because all the software, I assume, for enterprise will have to be revamped to move into in this realm.
So if you're talking about the basically kind of libraries or functions, I mean, we have a Qiskit, I haven't shown that here, but we have a Qiskit add-ons. So all the algorithms that we are developing with our partners will be ready to use. Just to grab it and then just plug it into your quantum program. There's a Qiskit functions, which is even more like a seamless integration of the entire workflow. So for example, like if you wanted to use SQD that we are using here to compute chemistry, SQD is actually offered as a free Qiskit add-on, but there are other startup companies working with us to provide you the whole package that you can just use the quantum computing algorithms easily. I think that's a little bit more, it's a commercial offering. But those are actually, we are doing together with our partners. And that's why the collaboration through the National Quantum Algorithm Center is very important, because we are really advancing the entire thing together. The system side of software, of course, IBM is doing it in certain part of it. And then the quantum and HPC integration, we are working with a lot of HPC centers. The RICAN is one of the prime example. Yep.
Okay, let's thank Hanhee for her incredible talk.